Okay, so last time you guys looked at the results of the Young experiments. We're going to look at the math and geometry behind it a little bit today, and we'll see how things all piece together. It's kind of neat, and let's sort of review the ideas we had last time. So we had the 1801 Young experiment to test for light, and of course the ideas were if light travels as a wave, it should, of course, interfere, and you should get a pattern out of it. Okay, so this will be really kind of cool. And of course, it was a big thing, and that's what we'll look at. So you can follow along in the sheet that you guys should have that was posted for you guys or I gave to you guys, and you can follow along and sort of fill things in as we go along, and things will work out okay. So the first big picture here is sort of laid out the experiment. I know in the simulation stuff that we had it going sideways, this is just sort of vertical, but we got the light source at the top. We got our two openings right there. We get the interference pattern as it goes, and of course this would be the detection screen, and we got a few things here that we are going to label. So first of all, the openings. We have the two openings, one here and one right there, and that is often labeled as the D value, the distance between them, because if you change the distance between the openings, you will get either a tighter pattern or a more widespread out pattern. The same way when you guys did basic two-source interference in general waves earlier on. Okay, now the waves of light, of course, then go and they hit that detection screen towards the bottom part. And the distance it actually travels is capital L, which is the length of the path between the distance or the openings to the actual detection screen. Okay. And then, of course, we get these little bright spots and dark spots at the far end. Right here, we got bright light, and there's no light on either side. And the distance between those bright spots is called the Y value, which is the distance between maximums, the different distance between minimums. And you can see they're numbered, and they're numbered. Now that's called the fringe number. That's what the fringe number is called, is sort of what count they are. Now it sounds kind of weird because the first maximum has a fringe number of 0. Now the reason why that is the fringe number actually tells you is how many waves or wavelengths difference there is between the distances. Okay, so let me explain this to you. So for the first one here, if we go right in the middle here, if this, let's say that's 5 wavelengths, that one would also be 5 wavelengths. That is 5 take away 5 is 0. It's perfectly symmetrical right in the middle. So the fringe number is 0 because it's the same number of waves. But if we go further out, if we go to this one over here, that distance and that distance, obviously the second distance is further, and it's 1 wavelength further, and that's why the fringe number is 1. This one here is 2 wavelengths farther away from the second opening compared to the first opening, and that's where the fringe numbers come from. Now this should sound familiar. It's the exact same idea that you guys did way back when you guys did basic two-wave interference, because it's the exact same idea. There was no difference. Okay, so if you went over here and you did S1 minus S2 divided by lambda, you would get a value of 1. If you went over here, you would get a value of 2, etc., etc., etc. If you went here, you would get 1.5 because it's at a minimum. It's the exact same idea. Okay, so that's where the fringe number kicks in. So you got to be it's kind of tricky sometimes because the first maximum has a fringe number of 0. The second maximum has a fringe number of 1. The third maximum has a fringe number of 2. These fringe numbers are always 1 less than which maximum minimum it is. So you got to be a little bit careful with that, but it's not too bad. Okay, so let's look at this a little bit more geometry-wise, specifically with what is actually going on. So that's where the second picture sort of kicks in. So sort of simplified. Instead of drawing waves, we've drawn wave rays to simplify it a little bit. There's the D value that we labeled, there's the L value that we labeled, and there's the Y value that we labeled. And you can see here, this one beam is going farther. This beam is going farther, and it's going n wavelengths farther. 1 wavelength farther, 2 wavelengths farther, 3 wavelengths farther, the exact same idea. Okay, so when we actually do the geometry of this, you can actually see we've got some perpendiculars, we've got some triangles being made, because triangles are made and we can use triangles to tie some ideas together. And there's basically two triangles being made. There's a triangle being made here, a little perpendicular triangle there, and we've also got a perpendicular triangle being made there. And the angles, the thetas labeled in each one, are identical to each other. We can go through all the fancy geometry, but we only have time and whatever through the video to do that, but just trust me, that's just the way it is. And it's kind of interesting because the two triangles can then be connected together with trig. So what we end up doing is we can actually create two similar right-angled triangles, and of course with this we can apply trig to them because we have right-angled triangles. So if we look at what we actually have in terms of measurements, the yellow triangle works really nicely. You got the little angle there. In terms of measurements, we've got the opposite is the n lambda, and that d would be the hypotenuse. So sine theta works really, really well. So if I did sine theta for that little yellow triangle, the opposite would be n lambda, whether it's 1 wavelength, 2 wavelengths, 3 wavelengths, whatever it is, doesn't matter, divided by the hypotenuse, which is the d value. And I can connect that to the blue triangle, do the same thing, where the opposite value, we'll connect it, the opposite value, or sine theta for my bluish triangle, the opposite would be my y values, and it could be 1 y value, 2 y values, 3 y values, it doesn't matter. Again, we're going to put a little n in front, and then that's divided by the hypotenuse. Now the hypotenuse is actually the average distance. This is the average of this distance from source 1 and the distance from source 2. It's the average of those two different distances. So the hypotenuse is actually the average distance the light actually goes. So now we've connected the two triangles together, we've connected the different properties together and measurements together. So we're not going to go through the whole derivation, all that kind of stuff. But if we then take this expression right here and we connect things together and we do some geometry and that type of stuff, we get a few things that actually can come out of it. First of all, we can look at the sine theta part. If we do that whole sine theta part is equal to n lambda over d, we can do the same type thing we did before. If the n value is an integer of some kind, this gives us a maximum. If it's n plus a half, this will give us a minimum, just like the type of stuff that you guys did before. All right. Now, if we start connecting the other stuff that's highlighted in green over there together, you can actually, use some geometry and a bunch of stuff that we're not going to get into. You actually get a nice ratio where lambda over y is equal to d over L. And that's just doing some geometry derivation stuff that we're not going to really get into. And if we just rearrange this a little bit, lambda is equal to dy over L. And then you can actually use this to actually find different wavelengths. And that's exactly what they did. So you could use this expression because you can measure the d value. You know how far apart the slits are. You could, once you have the detection screen, you can measure how far apart the bright spots are. That's the y value. And you can measure the L because you know how far the light went. They could then use this to find all the wavelengths of the different colors. So once you actually do this, this is actually used to actually find wavelengths of light, including all the colors and whatever else you want. This is how they actually did it. So it actually works out really cool in how it works. And it looks like kind of complicated stuff going on, but once you get into it and practice a little bit, it's not too bad. Okay, so we'll start practicing this and sort of show you what it actually can do. Okay, so we sort of have a couple of main expressions going on. The first one, lambda equals dy over L, is the basic Young expression that comes out of the experiment to calculate wavelengths and stuff like that. And then we've got the sine thetas for the geometry and angles that they go off at. You got the n lambda over d, that's for maximums, n plus a half lambda over d for minimums, because you want that extra half wavelength to get them to cancel out. So let's sort of show you how this all sort of ties together and how this actually works. So suppose, you have we got a set of openings or something like that, like this, and we are going to send some nice blue lights. We're going to use blue light through the openings, and when it goes through, it's going to make an interference pattern, get a bright blue spots in the middle, and then we will have bright spots going either side, all nice and symmetrical. And let's say that we put this together, and let's say these openings are 0.62 millimeters apart, and the light travels around 18 centimeters to get to the detection screen. And you actually do the pattern, you measure the pattern, and you find out that these maximums are 0.13 millimeters apart. Okay, so let's see if we can piece things together. Because what I want to know is, what is the wavelength of blue light? And this is literally how they did it. They did the experiments, took the measurements, and figured out. Well, let's see. Lambda is equal to dy over L. So if I piece this together, I can sort of figure it out. So I'm going to label my things. So this 0.62 millimeters, that is my D value. The 18 centimeters, that is my L value. That's how far the light went. And the distance between maximums is my Y value. So I have my D, I have my lambda, I have my D, my Y, and my L. All I have to do is put the values together, and I can calculate the wavelength. Now you got to be careful. You got millimeters, so you got centimeters, you got millimeters again. So make sure you watch your prefixes and calculate it out. So put it all together, you get around 4.48 times 10 to the negative 7 meters, which, well, that's a little bit of ugly meters right there. Meters, that's better, which would be 448 nanometers, and that's a good wavelength for blue light. Blue light's usually in the low 400s, so that's the wavelength of blue light. And this is what they did for every single color, and whether it's visible, not visible, this is how they mapped out the different wavelengths to see in spectrum charts and stuff like that. Now, when you're calculating this, you got to watch your prefixes. If you get the 4.48, that means you're doing the calculation in the right order. If you don't get times 10 to the negative 7, then you're just messing up a prefix or the scientific notation part. So the 4.48 is actually the most important part. We're getting the 448 nanometers. Okay, so that's literally how this works. Now, what about if we build on this and we what is the what's the angle to the third maximum going to be? So sometimes you look at the geometry and what direction this is going. So third maximum, well, let's see, the first maximum is always in the middle. This is my second maximum, there's my third. So that's the one I want. I want to know what is that angle right there. Now, there's a couple ways people do this. Some of you guys can probably see that we basically have a right triangle, something like this. So what some people will do is, especially if you have the y values, like there's a y value, there's a y value, and you know this distance, you can actually use tan theta to solve for it. You could do that. So tan theta, the opposite would be two y values, because that's a y value, that's another y value, and the adjacent would be the length. So you could do it that way if you want to. It doesn't make any difference. Or we could also use the sine theta expression we have up here. So we could also do sine theta is equal to n lambda over d. Now you got to be careful with the n value, because the n value is not 3. Remember, that's the fringe number, and the fringe number starts counting at 0. So that'd be 0, 1, 2. So that's where you got to be a little bit careful, because the n value is equal to 2. So you do 2 times the wavelength, which we found, divided by the d value, which we have over there, and you can calculate the angle. So sometimes people use tan theta, sometimes people use sine theta. It doesn't matter. Sometimes it depends on what you're actually given. But we'll just practice using the sine theta expression. So if we punch it all in, don't forget to inverse sine, we will get the angle. And we should get around 0.083 degrees. So typically we have pretty small angles. So they can look at the geometry of that a little bit, and that's how they can calculate the angles, which way the things actually are going to go. And this is how they can apply stuff using the Young experiment and the wave nature light. And of course, the biggest thing by far is those wavelengths. This is how they get all those wavelengths of all those different colors seen charts, and you can also do with X-rays and gamma rays and microwaves and whatever wave of light you want to use. You can use this to find their wavelengths, and that's how they get sort of mapped out the spectrum.